Hello, so here we are looking at GCSE Physics for CCEA 2015 and this is Unit 2. Question 4. The diagram below shows a transformer. From what material is the core of a transformer made? Okay, so we've got some options here. Copper is a non-magnetic material. Iron is a ferromagnetic material. Plastic is clearly not a magnetic material. And steel is a ferromagnetic material. The problem with steel is that it will not reverse its magnetism easily, but soft iron will, and so soft iron is the correct choice. Part 2. Complete the sentences about transformers. A something transformer gives a higher voltage at the secondary coil than the primary coil. So the secondary coil is the output. So something that gives a higher voltage at the output is called a step-up transformer. 2. The purpose of the core is to increase that would be the magnetic flux or magnetic field. And 3. In an electricity transmission system, there is a something transformer between the generator and the grid. This transformer allows the power to be transmitted at a lower current and therefore reduces the amount of something lost in the power lines. Okay, so this is what happens after the generator and before the grid. And if you remember from your notes, this steps up to a higher voltage, so it's a step-up transformer. And it reduces the amount of energy or heat being lost in the power lines. Okay. A transformer has 200 turns in its primary coil. The power supplied to the primary coil is 720 watts. The voltage across the primary coil is 240 volts. The current in the secondary coil is 0.05 of an amp. Assume the transformer has an efficiency of 100% and show that the voltage across the secondary coil is 14,400 volts. So firstly, they're telling us here the number at the primary, the power at the input, which will equal power at the output if this is 100% efficient. We've also got the primary turns and the secondary current. So we can use our output power equation. That will equal I at the secondary times V at the secondary. And so V at the secondary is going to be the output power over the current at the secondary. And so that's going to give us a VS of 14,400 like they told us. So now we're asked to calculate the number of turns in the secondary. So we have an equation that says that NS over NP, the numbers of turns on the secondary and primary, is the same ratio as the voltages on the secondary and primary. So NS is going to equal VS over VP times NP, just cross multiplying. You know, just multiplying both sides by NP to get NS on its own. And we know all those three things, so we can substitute those in. We know the voltage at the secondary, we know the voltage at the primary, and we know the primary turns. So NS is 12,000 turns at the secondary. Part B. A clamping ammeter such as that shown below is a device which measures electric current. It consists of an iron ring that can be opened and closed around a current carrying wire as shown in diagram A. A coil wound on the ring is connected to a meter as shown in diagram B. Explain why this type of meter will not work with a steady DC flowing in the wire under test, but will work with an AC. So what happens here is you've essentially got a transformer. The current in this wire produces magnetic field. That's picked up by the iron ring, and the changes in that magnetic field will then produce an EMF, which the ammeter then, it forms a little current, and the ammeter can pick that up. So this current will produce a changing magnetic field here only if it's an alternating current, so that the field is reversing all the time, because a transformer will only respond and produce an output at this end if there's a changing magnetism. So a steady magnetism will not produce an EMF, only a changing magnetism produces an EMF. And that's what we want to explain. So DC only produces a steady magnetic field in the iron loop, which will not induce an EMF. AC creates a changing magnetic field, which will induce an EMF and a reading then on the meter. Suggest an advantage of this type of meter might have over the meters found in school laboratories. Well, the big problem was when we try and measure current, we have to break into the circuit, and this doesn't require that. It reads the current indirectly from the outside without having to break into the circuit to measure it. And so the other advantage would be that this sort of non-contact method of measuring would make it much safer, because you're not having to actually make contact with the live circuit. Part 3 then, what would be the effect on the reading on the meter if the current carrying wire is wrapped several times around the iron ring? Well, obviously if you wrap more coils around the iron ring, you're going to produce a stronger magnetism in it, and so when it reverses you'll get a stronger change in the magnetic field, and that's going to increase the strength of the signal that you get, so you'll get a bigger reading. So we would expect a bigger reading to be observed. Part C then, the diagram below shows a loop of wire placed between the poles of a magnet. An electric current flows in the loop in the direction shown. As a result of this, some of the parts of the loop may experience a force. The magnetic field acts horizontally from right to left. Part 1, mark on the diagram above the north and south poles of the magnet. So they're telling us the field is going across this way, and field flows from north to south, so this must be the north and this must be the south. So then it says, use Fleming's left-hand rule to complete the table below to show which sections of the wire loop experience a force and the directions in which those forces act. So they ask us about AB, BC and CD. So for AB, you've got current heading backwards like that, and you've got magnetic field B going back across that way. So if you get your Fleming's left-hand rule lined up with that, you're pointing with your left hand, make a gun with your left hand, point it to the left of the page, and then stick your second finger out to represent current. You'll find your thumb is pointing straight up when you do that, so there's an upward force on that side. Now we'll leave BC for now, but if we go to CD now, current is now coming backwards that way, with magnetic field still going across that way. Now, for that to happen, you need to twist to get your field still pointing across with your pointing finger, and your current coming back towards you. You have to tip your hand upside down, and that means that your thumb is now pointing straight down in that position, so the force on that one would be downward. Now as for BC, what you've got with BC is current. Sorry, that's not current, that's magnetic field. Magnetic field running like anti-parallel to current. Now, if the current isn't crossing the magnetic field, there will be no force. So in BC here, there would be no force. But in both AB here and CD here, there would be a force in both of those cases. So we now need to fill that in the table. So for AB, it's yes, and it's up. For BC, it's no, and you can just leave that blank. And for CD, it's yes, and it's down, because that agrees with what our Fleming's left-hand rule gave us in all those cases. So upwards at AB, no force at BC, and downwards at CD. Okay, part 3 then. A student reverses both the direction of the current in the loop and the polarity of the magnet. What effect, if any, will these combined changes have on the direction of the forces in the loop? So reversing one of these things would reverse the direction of the force, but reversing both of them will bring the force back to its original direction. So there will be no effect. The forces will be in the same direction as the table shows. And that's that.